Okay, so now we're going to be, let me give it a second, actually. Give it a second to load. Slowly, we're getting there. Hold on. Sorry about that. Everything was lagging a little bit. Hopefully we're good now. We're good now, yeah? Yeah, everyone's good? Okay, let's get started then. So, here, the states of matter, so as we know them, they are solid, liquid, gas, and plasma. Technically, that is the ones that really exist here on Earth under normal conditions. However, there's actually a total of 22 different states of matter that have been described by scientists. Really, if you change the temperature and pressure, you can get all sorts of different states of matter. Okay. Thanks. Yeah, I had to get out of the meeting, so I stopped presenting. It'll take a second to present, but I really wasn't talking about anything on the slides anyway. But I'm just talking about the states of matter in general. Everyone's pretty much aware of solid, liquid, gas states of matter, and plasma. Those are the ones that we find typically on, in everyday occurrences, right? Table is solid, water is liquid, air is gas, and then plasma is the stuff in like the fluorescent light bulbs. That's actually plasma. So things that you see like every day, those are the three states of matter. But there are other states of matter. There's actually, like I said, 22 states of matter that scientists have figured out. And again, it's all due to temperature and pressure changes. We can change states of matter due to temperature and pressure changes. Okay. But ultimately, what really decides the state of matter at a given temperature, there's two factors. Okay, so the states of matter can be explained by these two factors here. The first one is intermolecular forces. Intermolecular forces explain how particles interact in a system. Inter means between, and force means a push or pull. So we're talking about pushes and pulls between molecules. So pushes and pulls between molecules. How are they attracted to one another? And then the second part is related to kind of like the amount of energy, the amount of kinetic energy that each particle has in a system or in a given object, right? And kinetic molecular theory, kinetic means motion. It means motion. Molecular means a molecule. So motion of molecules, and theory is a explanation. So an explanation based on multiple studies and multiple scientific experiments. Always correct there. So basically, kinetic molecular theory is the explanation of molecular motion. Explanation of molecular motion. Intermolecular forces are the forces between molecules, or push and pull between molecules. Okay. So those two things really help us to explain and understand the states of matter, why certain things are in the state of matter that they are in. So basically, the state of matter is determined by how strongly things are attracted to one another and how fast the particles are moving. Okay, so let me distinguish here first between intermolecular forces and intramolecular bonds. Okay, so you'll hear these two terms. We'll talk a lot about intramolecular bonds in the next unit when we talk about ionic bonds, covalent bonds, and metallic bonds. Those are intramolecular bonds. Those are, intra means within, so within molecules. So bonds within molecules. Intramolecular bonds, bonds within molecules. Okay, these are the things that determine chemical properties. So intramolecular bonds determine chemical properties. Whereas intermolecular forces again are the push or pull between molecules. Push or pull between molecules. And those determine physical properties. One of the physical properties of matter is state of matter. Okay, state of matter. So intermolecular forces, they determine physical properties. Intramolecular bonds determine chemical properties. Okay, moving on. Again, this will be up, so if you missed something, feel free to go back to it. Okay, so now let's talk about kinetic molecular theory. So actually, wait 1 second. Intermolecular forces, the stronger the intermolecular forces, the more likely something is to be a solid. Okay, the weaker they are, the more likely it is to be a gas. Okay, so the stronger the connections between the molecules, the more likely it is to be a solid. And then the weaker the connections, the more likely it is to be a gas. Okay, that's one factor. The other factor is this kinetic molecular theory, the motion of the molecules in a substance. So there's three assumptions. We're gonna talk about each assumption individually, but I want to go over them really quickly. So the first one is that all substances are composed of particles, and all those particles are in constant motion, even in solids. The only time particles have no motion is at 0K, or absolute zero, right? So that's when all molecular motion stops, absolute zero. And if you remember, Bill Nye said that we can never actually get to absolute zero because everything is connected to everything else. Okay, and that is kind of true. We've been able to get scientists have been able to really get really close, but never actually get to absolute zero. Okay, number two, collisions between particles are perfectly elastic. That means this is basically just the conservation of energy. Okay, so that when two particles collide, the total energy going into the collision is equal to the energy coming out of the collision. No energy is lost or gained, lost or gained during that collision. Okay, it may be exchanged between particles, but no energy is lost or gained. The total energy. And then last is really a definition of temperature. What is temperature? Well, the average kinetic energy of the particles is proportional to the Kelvin temperature. So it's basically the temperature. When you take the temperature of something, you're taking the average kinetic energy of that system. You're finding the average kinetic energy of it. Okay, we're going to talk about each one of these individually. So let's first start with the states of matter. Okay, so the states of matter, the particles in a substance are always in constant motion. Particles in a solid, they vibrate back and forth, so it may seem like they're just not moving at all, but they actually are vibrating and rotating and turning. Okay, so they're vibrating back and forth. In a liquid, they're flowing past one another, so they're kind of moving past one another. Their intermolecular forces are temporarily broken. In a solid, the intermolecular forces are maintained. They're not broken. Okay, they're not broken. In a liquid, they're temporarily broken and then remade as the liquid flows past one another. Okay, a gas we consider to have like no intermolecular forces, none to very little. Okay, so the gas particles are just bouncing around like crazy. They don't really have any attraction towards one another. There really are no intermolecular forces between gases. It's very, very little, very, very little. So that's the first one, that all particles are in constant motion. The only time they are not in constant motion is at absolute zero, at 0 Kelvin. We call that absolute zero. The second one, again, is that collisions between gases are perfectly elastic. Okay, and really all collisions in any object are perfectly elastic, not just gases, but liquids and solids. So the collisions between gas particles result in no net gain or loss of energy. The energy can be transferred from one gas particle to another, but the total amount of energy remains the same. Okay. So the speed at which the particles move may change, or that may change, but if one particle loses some kinetic energy, another particle gains that same amount of kinetic energy. So it's always just transferred from one to another. Okay, and the last one here is that the average kinetic energy is directly proportional to the temperature in Kelvin. Okay, it's important that we say Kelvin because it's not the same for Fahrenheit. Fahrenheit's not directly proportional. Fahrenheit's a little bit different, just the way the scale is. Okay, now temperature actually measures the average kinetic energy of all the particles in a substance. Okay, not all particles have the same amount of kinetic energy in a substance. Okay, some particles have very little energy, some particles have a lot of energy, and most particles have somewhere in the middle. Okay, but when you take the temperature of it, you're looking at the average kinetic energy of it. And the general rule of thumb here is that if we change the temperature by 10 degrees Kelvin or 10 Kelvin or 10 degrees Celsius, 1 Celsius is the same as 1 Kelvin, the kinetic energy doubles. So 10 degrees Celsius is a change of double the kinetic energy or half the kinetic energy if you go down. Okay, now this chart here is called the Maxwell-Boltzmann distribution curve. And this is a representation or showing of the molecular speed on the bottom axis here, or on the x-axis, and the number of particles on this one. You'll notice that as the temperature increases, so we start at 100 K with this like aqua one, most of the particles have very slow, they're moving very slowly. That's because it's cold. It's colder, right? It's pretty cold. So if something's cold, most of the particles are going to be moving rather slowly. But as we increase temperature, more of the particles are going to be moving fast. Okay, so and then getting hotter and hotter, more and more of the particles are moving more and more quickly. So you'll see even at a high temperature, there are some particles that are moving rather slowly. And even at a low temperature, there's some particles that are moving rather quickly. Okay, so again, not all particles are moving at the same speed. It's just that when we take the temperature, we're looking at the average kinetic energy of the system. We're going to come back to this Maxwell-Boltzmann distribution curve when we talk about evaporative cooling. We'll probably talk about that Tuesday or Wednesday next week. Okay. So now talking temperature scales. In the US, we're pretty used to using Fahrenheit, right? We use Fahrenheit to tell our everyday temperature. And it kind of is a little bit better of a scale because for at least temperature-wise, because each degree Fahrenheit is actually smaller than a degree Celsius. Okay, it's actually more precise. You're moving smaller increments as you move degrees Fahrenheit. So the difference between 94 and 95 degrees Celsius is much larger than 94 and 95 Fahrenheit. Okay, it's actually like twice as much. Okay, but 1 Kelvin and 1 Celsius are the same amount, the same movement amount. Okay, and that's what this kind of chart tries to show here. Okay, if you look at Celsius at 0 degrees Celsius, 273 K, and then go down to 0 K, so that's minus 273. That's the same amount if you go from 0 to minus 273 for the Celsius scale. So it's very, very similar here. It's pretty much the same. 1 Kelvin and 1 Celsius are pretty much the same. Okay. Whereas if you go Fahrenheit, 32 to 460 is a much larger number gap, but it's the same actual temperature gap. Okay, so the number of degrees, there's more degrees Fahrenheit change here than there is Celsius change here, but the amount of kinetic energy is the same. The change in kinetic energy is the same. Okay, it's good to know these different, really the freezing point and boiling point of water for in degrees Celsius. It's really, really simple. 0 Celsius is the freezing point and 100 is the boiling point. That's the normal boiling point. The boiling point at atmospheric pressure. At sea level, I should say, at sea level. All right, converting between units, you're just going to be using these formulas. I always give you the formulas on a test or quiz. You don't have to memorize them. I think if you use them enough, you start to memorize them and understand them, but it's a little bit tricky sometimes. So here, Celsius is equal to 5/9 times, and then you have to take the Fahrenheit temperature minus 32. So take the Fahrenheit temperature minus 32, then multiply it by 5/9, and you'll get the Celsius temperature. Then Fahrenheit is equal to, you multiply 9/5 times Celsius temperature, then add 32. And then Celsius to Kelvin and Kelvin to Celsius is really, really simple because those are the same. It's 1 degree, 1 Kelvin is equal to 1 degree Celsius. For Kelvin from Celsius, you just add 273. And from Kelvin to Celsius, you minus 273. And we don't say degrees Kelvin, we just say Kelvin. I always mess up and say degrees Kelvin, but it is just Kelvin. There's no such thing as degrees Kelvin, it's just Kelvin. That's it. I'm going to stop there.